Hi everyone, my name is Neha Kardam and this is the ninth lecture on electronic communications. In this lecture, we will learn about frequency modulation receivers. So let's get started. Now what is frequency modulation? It says frequency modulation is a method of impressing information onto a radio frequency carrier signal. And we know that this frequency modulation is a fundamental technology like amplitude modulation. And its techniques are used in satellite, data communications, telemetry, and other non-broadcast applications, for example, music synthesis, video transmission. And it is also used in magnetic tape recording system, radar, and in the medical industry also, for example, in EEG monitoring of a newborns. Let's read further. It says in FM, the frequency of the carrier signal is changed in steps with the information. And because of this, the FM receivers must use a different method of demodulating the signal than that used by AM radios. So you know that in frequency modulation, the frequency of the carrier signal is basically changed, and it is different compared to the amplitude modulation. And in the amplitude modulation, the amplitude of the carrier signal was changed. So here the demodulating techniques are going to be different than the AM demodulating techniques, because here we are changing the frequency, not the amplitude. So let's see further. Now, how to receive an FM signal. So here on the screen you see the block diagram of FM receiver, and these the blocks which you see with this blue color, these are the basically new addition to the AM receiver. So I'm gonna explain each of these blue blocks which you see in this block diagram. First, I'll start with the detector. So this detector's circuitry is going to be different than the demodulator you saw in the amplitude modulation. And the function of this FM detector is to basically convert the varying input frequency into the varying output voltage. Now let's talk about the limiter. So ideally in frequency modulation, the carrier wave amplitude, you know that it remains constant, which means that the transmitter does not amplitude modulate the carrier and the envelope, which carries no information. However, between the transmitter and the receiver, there are various sources of external noise which can come in the transmission, and these noise could be such as atmospheric noise or man-made noise sources. And when these noises added at random to the voltage of FM signal envelope, then the signal at the output will look like something like this, which you see here. So like in AM receiver, it is quite affected by these noises, but in FM signal it is not that much affected by the noises. And so that's why we use here a limiter, and with the help of limiter it flattens the top and the bottom of the modulated wave. So you see here, after using the limiter, the waveform will look like this. Flattens the top and bottom of the detected output voltage waveform, and it eliminates most of the noise but preserves the information, and that is why FM receivers is free from any static interference, and the detector sees only the frequency change in the modulated waveform. So hence we can say that the FM receiver can safely ignore all amplitude changes without losing any information with the help of this limiter. Now next comes is the radio frequency amplifier. So this radio frequency amplifier basically provides two important purposes. First is for it is used for amplification, and under that we say that the signals from antenna are, you know that they are very tiny. When you receive the signal over here, the magnitude of that signal will be very small. It will be in like a few millivolts or few microvolts. So this small signal is mixed with the local oscillator here. When it is mixed with the local oscillator here, it can be easily lost in the noise from the mixture when it comes here. So this mixture basically adds considerable inherent noise to the signal that passes through it. If you talk about in amplitude modulation, then there it is not a problem, as the signal levels which are received at the antenna, they are in hundreds of microvolts. But in frequency modulation it is a problem. So that's why these RF amplifier, you see, they provide sufficient gain for the incoming radio frequency signal to overcome any noise floor of the mixture. Now the second purpose of this RF amplifier is that it can be used as a local oscillator energy separation. So you know that in the local oscillator, the power levels are in between from 0 dB to 10 dB, which is like very small. So what would happen if local oscillator output it gets coupled to an antenna? Then in that situation, your receiver basically behave as a transmitter. So in that case, receiver can become quite a potent interference source, and that's the reason we use radio frequency amplifier, which prevents the local oscillator re-radiation by allowing the signal to flow only in one direction from antenna to the mixture. Now next is the AFC low pass filter. So this AFC basically stands for automatic fine control low pass filter, and this AFC circuit under this block, it is used in situation where you must accurately control the frequency of an oscillator by some external signal. Now this the receiver's frequency, it basically drift rapidly, and it degrades the quality of the FM reception, and that's why we use this AFC low pass filter. It basically corrects the local oscillator drift. So what exactly happens here? As the receiver's frequency drifts off, then what will happen? A positive or a negative DC voltage is produced at the FM detector, and this DC voltage is fed back to the oscillator, which basically pushes the local oscillator back in the correct direction. So here this low pass filter, it is included here so that only steady DC is sent to the local oscillator circuit. And this local oscillator circuit you see here, it consists of a reactance modulator, which converts DC AFC voltage, automatic fine control voltage, into a varying capacitance or inductance, which corrects the oscillator frequency. Now let's see next. So next is it says most FM receivers use super heterodyne technology. So what you see here is the super heterodyne technology, just like AM. The only difference is these blue blocks you see in this block diagram. These are the new thing which is added to the FM receiver, and this second line says the same thing. Now here there is one more thing to keep in mind. So like an amplitude modulation receiver, in that we used to use automatic gain control, whereas in frequency modulation receiver we do not use this. We do not use the automatic gain control. Let me first explain what is automatic gain control is. Automatic gain control is basically a circuit designed to maintain the same level of amplification for sound or radio frequency, and if the signal is too low, the automatic gain control circuit, it will increase the level, and if it is high, it will lower the level to maintain a constant level as possible. And this automatic gain control is widely used in AM receivers. And in FM, we don't use it because FM don't respond to amplitude variations. And FM receiver, here you see it has a limiter. And this limiter basically removes any variation. Therefore, FM receiver don't need automatic gain control. However, in some cases where FM receiver must operate over a wide range of antenna signal voltages, in that situation we can use the modified form of automatic gain control, and that modified form of automatic gain control is called as delayed automatic gain control, and the short form for that is DAVC. Now moving on to the next slide. FM receiver block analysis discuss why the following stages are new or different in an FM receiver. So we know what are those stages are. RF amplifier, IF limiter, detector, automatic frequency control. So these we have already discussed. So I'll move on to the next slide. Now comes the method for FM detection. So there are several methods which are there, and I'm going to discuss all of them one by one. Let's read here. It says FM detectors use a wide variety of methods. Some aren't very practical, such as slope detector, but demonstrate important principle of operation. So yeah, this is the first method which we are going to discuss, is the slope detection method. So yeah, these are the four methods, and first method is the slope detection method, and it is not a very practical method. We are going to see the circuit for this one, and it converts the FM signal into AM, then enveloped detects it. There's a mistake over here. Second is the Foster-Seeley detector. This is another method, and in this method it truly high fidelity FM detector, but very sensitive to AM noise, and it converts FM to phase modulation. This PM is basically the phase modulation, and then from phase modulation it converts into amplitude modulation, and this is the way it detects it. And then third one we have is ratio detector. In ratio detector, it is derived from the Foster-Seeley detector method only, and what it does, it mostly rejects the high frequency amplitude noises, but still requires effective limiting. So we're going to see this also. And then last is the quadrature PLL. PLL, you know, it stands for phase lock looped, and this is the these two. You see here, these two are the two different methods, quadrature and the phase lock loop. So these two methods of FM detection can be used, and these are the modern types of methods which are built on a IC chips, and PLL, which you're gonna see, can be built entirely on a small chip. So let's go ahead and see how the circuit looks like for slope detection method. So you see here a slope detection method, and in this the input signal is basically fed from here, and we see here this is the information signal, and this is the carrier signal, and this carrier signal is varying based on the input signal. So when the input signal is positive, you see that you get the maximum frequency, whereas when it is negative, you get the minimum frequency. And whenever the information signal crosses the zero, at that point your frequency will be equal to the carrier frequency. So let's see the circuit diagram. In the circuit diagram, you see this transformer over here. So this transformer is basically behaving as a frequency selective circuit. So you can, if you want to understand, you can divide this whole circuit into two blocks. The first block would be this, you see here, and this block is for frequency selective circuit, and the other block, which consists of this diode, capacitor C1 and R1. This other block is basically your envelope detector. So with the help of frequency selective circuit and the envelope detector, we can basically demodulate the signal in the frequency modulation. And here at the bottom you see this is the frequency selective network's characteristic based on this tuned circuit, and this characteristics is drawn between the gain which is on the vertical side, gain versus with respect to the frequency. So gain and between gain and frequency, the this characteristic graph has been drawn. And when the FM signal gets coupled, FM signal which you are getting it from here, gets coupled with the tuned circuit, then we get this type of characteristic graph. Now here, this is the frequency when your amplitude is maximum. This is also called your resonant frequency, and this resonant frequency will be greater than the input frequency which you see here. So this represents your input FM signal which goes into the frequency selective circuit. Now what will happen when the signal goes into the frequency selective circuit, then after coming out of this frequency selective circuit, the amplitude modulated signal is basically obtained over here, and that amplitude modulated signal is passed through this diode. Then the waveform obtained here is obtained here. You can actually detect the envelope of that waveform. Now here, if the resonant frequency which you see here of the tank, if the current frequency you see here, it increases, then the resonant frequency also increases. And if the current frequency of the input signal, it decreases, then the resonant frequency also decreases in this circuit. Now this method is not practical, and there are two reasons for that. First is the 2 points which you see here on the characteristics on the tuning curve. You see that that will provide a dual response. That will you can see the second possible active region we can find over here on the other side. So it provides the dual response, which is basically ambiguous tuning characteristics, we can say. So this dual response is not desirable. It is not good for the detector, because you will not be able to get the right signal. And the second reason is the frequency response which you get is not linear unless only small portion of the curve is used. So for wideband FM detection, this method would not actually work very well. Now let's see the other method, which is let's first read down what it says. The slope detector works by converting the FM to AM. So we saw that already. And using the frequency response curve of the detector tuned circuit, it has a dual response, which isn't very practical and produces large amount of distortion, hardly a hi-fi circuit. Now let's see Foster-Seeley detector method. This Foster-Seeley detector method, it converts the incoming FM signal into a series of phase shift. So this the circuits you see here, these types of circuit are used in Foster-Seeley method. The second circuit is the modified form of this, and these two circuits are still not a practical circuit. We will see the more practical circuit later on in the slides. But let's first understand this circuit. It has a transformer here and a reference frequency we get from this oscillator, which is connected to the center tap of this transformer, and from here we get the input FM signal. So this input FM signal is basically coupled into the transformer T1, whose secondary is basically secondary of the coil is parallel resonated by this C1 capacitor at a center frequency, or we can say the intermediate frequency. And for FM broadcast, this intermediate frequency is 10.7 megahertz, which is the standard value. Now this capacitor you see here, C1, and the secondary and the inductance of the inductance in the secondary coil of the transformer T1, they form a phase shifter circuit. This and the inductor here, they form a phase shifter circuit. So actually what happens, a steady sine wave at the center frequency of 10.7 megahertz produces a voltage of VC. So this VC you see here, it produces a voltage of VC which is applied to this center tap of T1. And at rest, when this the carrier frequency is equals to when this carrier frequency is equals to the frequency of this tank, and at that time the phase shift is adjusted to be 90 degree by tuning this T1. So at the output of the top output here, you see you will get the phasor sum of voltage VC and this VA. A voltage VA will be developed over here and VB voltage will be developed over here. So at the top of this you will get VAC voltage, and at the bottom you will get VBC voltage. So this VBC voltage will be developed over here. So this phase relationship between VA and VB, they are 180 degree out of phase. So when frequency is equals to carrier frequency, then in that case the circuit is balanced, and the outputs VAC and VBC you see here, they both will be equal in magnitude. And if their absolute values are subtracted, then you will get the zero value. Now what will happen if the input frequency rises? If the input frequency here rises, then what will happen? So in that situation, the rectified output VAC will be greater compared to the VBC. So I'm talking about the case when the input frequency is higher. So in that case, your VAC will be greater than VBC. And you will see the opposite effect when input frequency is lower. So when input frequency is lower, in that situation your the voltage which is obtained here, VBC, it will be higher compared to your VAC. So the second circuit you see here, this is used to detect the out of balance condition, and out of balance condition is that when frequency changes, it goes high and low when the circuit is not balanced, which means it is not VAC is not equal to VBC. So in that out of balance condition, you use this second circuit where you see these two diodes are added, and this extra circuit which is the resistance and capacitor, they are added over here. So here the function of this diode is to rectify the AC voltage which is coming out of this point and this point. So it will rectify the AC voltage VAC and VBC, and the algebraic output of this will be basically you will get over here through this capacitor VAC, absolute value VAC and absolute value VBC. So when the input frequency, in this case, if the input frequency rises, the rectified output, this VAC will be larger than the VBC. So you can say mod of VAC minus VBC when the frequency is higher. And when the frequency is lower, the opposite effect can be seen when the carrier frequency is lowered. Now in that, when the carrier frequency is lowered, in that case you will get mod of VBC minus mod of VAC, because VBC will be higher in that case. So that result you will obtain over here. Now let's see next. So it says the Foster-Seeley circuit converts the FM into phase modulation. It then phase detects the information. The circuit shown above shows, so we are talking about this B circuit, shows how the phase information is converted to an instantaneous voltage representing the information. So here you see that how the frequency is changing, and as the frequency changes, the voltage obtained over here changes, and which represents the change in the phase. Now this this picture you see here, it basically shows the relationship between the phases VAC and VBC. So in the first case, when the circuit is balanced, when input frequency is equals to carrier frequency, in that case, your VAC and your VBC, these two voltages are going to be equal. Whereas when input frequency is higher, then you know that, as I told you, VAC, the magnitude of VAC will be higher, and that's why it is shown like this, and the magnitude of VBC will be smaller. And in the third case, when input frequency is lower, then your the magnitude of VBC will be higher, and for VAC it will be lower. So let's read here. So this red VC vector is the reference oscillator output. It never changes in phase. So as you can see, it is not changing in all these three conditions. So VAC and VBC take turns getting larger and smaller as the FM signal moves up and down in frequency. By summating the VAC and VBC vector, we convert the instantaneous phase of the signal back into a recovered information signal. Now, the practical Foster Seeley detector doesn't have a reference oscillator, which we are going to see next, and the vector VC actually rotates in a real circuit, but not as much as the vector VA and VB, since VC passes through a circuit of a lower order. So this circuit, the practical circuit, now we are going to see next, and in that circuit, the reference oscillator which you saw in the previous circuit, you see over here, from here your VC reference voltage was created through this oscillator, and in the practical circuit, this reference oscillator has been removed and it has been replaced by this inductor, and it is coupled through this capacitor C. Now here, as you know, as I told you, the oscillator is replaced with a sample of a RF carrier voltage, and that RF carrier voltage serves as a reference voltage, and this voltage is basically developed by using this C4 and inductor L1. So when the input frequency changes, then what will happen? The L1 also changes its phase relatively slowly, and the voltage across L1 is your reference voltage. So previously you saw it was developed through the oscillator, but here now the reference voltage is developed using this L1, and that will be your approximately reference voltage. And now further, the resonance circuit here you see is consists of this transformer secondary here connected to the C1, which changes the phase more quickly because it has two reactive parts, and therefore for practical purposes the phase change across L1 is small enough to consider that portion of the circuit to have an approximately constant phase angle. So similar to previous circuits, a voltage VA and voltage VB will determine the magnitude of the voltage output from the detector. And if input voltage of the FM signal changes, or if the frequency of the signal changes here, then these vectors which you obtained over here, so here you will have VA and VB, and then here finally you will get VAC and VBC. So these vector will change in the voltage vector which you obtain over here. They will change in size, and the detector's output voltage it will change accordingly. So this Foster Seeley detector, it does not reject the EM amplitude modulation, and which is basically the disadvantage, since most noise are in the form of amplitude disturbance. So to prevent this, limiter stage must be used to prevent any noise, any amplitude modulated noise from reaching out to the circuit. So you can use the limiter, And there are some advantages of this circuit. It offers a good level of performance and resonance linearity, and it is easy to construct using the discrete components like your inductor and capacitor. And the drawbacks are it is not suitable to use for IC technology. It is not very compatible, and the cost of making the circuit is also very high. And the last one I already told you is the noise, and for that you can use the limiter circuit. So let's quickly read what it says here. The practical Foster-Seeley circuit has inductor L1 instead of a reference oscillator. The reference voltage VC is developed across L1. This reference voltage is of approximately constant phase when compared to VA and VB. And because VA and VB must traverse the second order resonant tank, two-pole T1 and C1, while VC must only pass across L1, one pole, for above the operating frequency. So now moving on to the next slide. So here, this is the third method of FM detection technique, and this is called ratio detection. The ratio detector is the modified form of Foster-Seeley detector. And one of the diode here you see, if you notice, compared to the previous method here, this diode is reversed. So in the previous one, you see they are in the same direction, whereas in the ratio detector, one of the diode is reversed. So notice that the voltages because of this they are going to be different. So here you will get the same voltage VAC, but here you will get the negative VBC voltage at the bottom of the circuit. And this R1 and R2, they form a voltage divider circuit. So when VAC and VBC are equal, the output voltage from the divider, it is going to be 0. And when VAC is not equals to VBC, then the positive or the negative voltage output is produced upon. Now another addition to this circuit is the capacitor C5, which you see over here. And this capacitor is basically an electrolytic capacitor, and it has value around 10 microfarad, and it tends to stabilize the total voltage across this circuit. This is actually a primary addition to this circuit when compared to the Foster-Seeley circuit. So with the help of this capacitor, the sum of these two voltages is going to be constant. You are going to get the constant voltage even when the circuit is unbalanced. Now let's see further. The ratio detector circuit keeps a total voltage across R1 and R2 constant by the filtering action of C5. So we have discussed this just now. The ratio of the voltage across R1 and R2 varies in step with the information, but the total of these voltages is always constant. Now the another circuit which you see here of a ratio detector, and if you notice here, the addition is this transformer T2, and previously we had this just one transformer, and this is another circuit where we have the second transformer, which is T2 transformer. So this T1 and T2, they usually match a set of transformer designed especially for ratio detector, and they may even be contained in one metal can with the two screw adjusted visible. So this T2 you see here, it will produce the output voltage VC, which is our reference voltage. So that is the only new addition into this circuit. So the secondary of the T2 is used to provide the reference voltage VC in this one. Now, now the last method we see here is the PLL FM detection. And PLL you already know. We have seen this this block diagram before also. PLL is phase lock looped, and the Foster-Seeley and ratio detectors are excellent FM detectors, but they require use of RF transformer. So with the help of this PLL, and the help of PLL, you don't have to use those transformers. And in this type of detector, it can be used as a FM detector by just extracting the audio signal at the low pass filter output. So the PLL which you see over here, it is a closed loop system, and whose purpose is to lock its oscillator onto a provided input frequency. And you already know that it has three basic blocks, which is loop low pass filter, VCO, voltage controlled oscillator, and the phase detector. Phase detector, you know, it is used to compare the FM input, sometimes referred to as the reference signal, to the output of the VCO. So input signal is basically fed from here, and the signal which is obtained from VCO is from here. So these two are compared. And this VCO frequency, you know, this is varied by the DC output voltage from the low pass filter, and this low pass filter uses to smooth, it basically smooths the output of the phase detector into a control voltage that varies the frequency of the VCO. So as the primary job with this phase detector, you know that it will compare the two input signals, and it will generate an output signal that when filtered will control the voltage controlled, will control the VCO. If there is a phase or frequency difference between the FM input and the VCO signal, the phase detector output varies in proportion to that difference, which is obtained from here, and the filtered output adjusts the VCO frequency in an attempt to correct for the original frequency. And when no input signal is applied, the phase detector and the low pass filter, their output, they are going to be 0. So this PLL is basically the excellent FM detector, and it can be built without any without using any radio frequency transformers, whereas in the previous methods you saw that we had to use the transformers. So in this one we don't have to, and in fact all of the circuitry, it can be built on a single chip. So let's see what it says over here. The PLL FM detector can be integrated onto a single IC chip. Bulky coils and transformers are entirely eliminated. It works by normal PLL action. The VCO follows the input frequency according to the correction voltage from the phase detector. The correction voltage becomes a copy of the information signal because of the following action. The VCO must have very good linearity for the PLL detector to have a low distortion. Fortunately, this is quite easy to achieve. Now next is the quadrature detector method. It is a digital frequency modulator detector circuit, and like PLL, it provides built-in limiting action through a Schmitt trigger input, and can be implemented on a integrated circuit. In this circuit you see here, it has a XOR gate which functions as a phase detector, and this R1 and L1 you see here, this is called your this whole coil with the capacitor is called quad coil. They form, this R1 and this L1 quad coil, they form a phase shifter network. So as the FM input signal changes in frequency, the phase shift is developed across this R1 and L1, and L1's this L1's internal capacitance, which you see here, this will also vary, and this causes the phase of these two signals which you see, one is going over here and the other is going from here, at the phase detector XOR gate to vary. And this in turn causes the duty cycle of the pulses at the gate output to vary, and then the gate output converted to a DC level into a DC level by the filter, this R2 and C1. The DC levels has information riding on top of it. So this C2 basically is used to remove the DC level, and rest over here we can recover the information signal. So that was the working, and now let's quickly read what it says here. The quadrature detector uses R1, L1 and the capacitor internal to L1 to convert the FM signal into the phase modulation, or we can say PM. The phase shift is then converted into information by phase detector exclusive OR gate U1. The detector requires L1, which is a discrete coil unit. So we are talking about this coil, quad coil. So next you see here is the synthesized FM receivers, and this synthesized FM receiver, it uses the frequency synthesizer here. We can say frequency synthesizer local oscillator instead of a LC oscillator, LC controlled oscillator. So like most PLL synthesizers, they require a relatively low yet stable reference frequency. So to avoid that problem, what we can use the crystal oscillator, and we have discussed this in the previous lecture also, that crystal oscillator, you know, that it provides stable frequency, so we can use that here. And when you use the high frequency crystal oscillator, they are also called master oscillator, and that master oscillator, it divides the frequency down digitally until the desired reference frequency is obtained. So I hope you remember the circuit back in PLL lecture. So here you see the microprocessor, it issues the commands to the various parts of the PLL by sending the digital values to each of the PLL registers. Here this local oscillator FLO, which you see here, local oscillator frequency, is controlled by this microprocessor, and the pre-selector here should electronically track the local oscillator with this local oscillator frequency, so that the frequency difference of FIF, which is the intermediate frequency we obtain from here, can be maintained. And there are two ways of doing it. First is either using the software to drive the digital to analog converter and use the resulting voltage to tune this pre-selector. And the second method is by using the voltage controlled oscillator, where voltage controlled oscillator, you remember, we use VCO to track local oscillator frequency if there is any change in that. And as the local oscillator frequency increases, the VCO control voltage also used to increase, and if that increase is if that increase is sent to the pre-selector, the pre-selector resonant frequency will also rise. So the VCO is basically tuning both the local oscillator and the pre-selector. So two ways you can use, by the software and by using the VCO. Now so I'll not get in detail of the whole working of this, because we have covered the similar block diagram in the previous lectures. So today all of this circuit, the block diagram you see here, they can be built on a simple one or the two IC chips. So IC chips. So you can imagine that how drastically the circuit can be reduced. So I'm quickly gonna read here. It says many modern receivers are synthesized instead of a manually controlled local oscillator and a preselector. They use a PLL or direct digital synthesized derived local oscillators. Microcontroller provides the user interface and operate the PLL. These receivers don't usually require AFC, automatic frequency control, and due to excellent frequency stability of the PLL synthesizer. An exception to this might be a satellite or other microwave receivers, which may have to compensate for Doppler shift from a moving transmitter. So maybe in those cases you can use the AFC. Now summary, I'll just quickly go through each of these points, and this summary covers what we have done in today's lecture. And it says FM signals are created by changing the frequency of the carrier in step with the information signal. So, and that is what our FM frequency modulation is. So we learned about a super heterodyne receiver topology, and it is used for most FM receiver, which changes to accommodate FM modulation. And then we saw most of FM detectors, which converts the FM to AM, then detects the AM signal. And next is practical FM detectors include the Foster-Seeley ratio, detector, quadrature, and PLL other methods we have seen. And then synthesized FM receiver use a microcontroller to operate a PLL, which in turn acts as a local oscillator. So this is the end of the lecture. Thank you so much for watching it.